Nothing like a technical issue to keep your adrenaline very high. Um, I'm really glad to be here. Thanks for everyone for having me here. It's not easy, second day conference. I hope everyone's having fun, but maybe yesterday night some of you may have too much fun. So, but anyway, let's go. I'm gonna talk about a little story here about SQL databases and a story around a product that I work on. When I was building those slides, though, I noticed that the wordplay that I use is kind of wrong. I should use an your instead of a. I don't know if it's actually a wrong thing or just a little mistake, but the thing is, English is very hard. And that's why I feel that a conference like this is very important to us as a means to practice, not only here on stage, but in every place here in the conference. And it's important as well to give this showcase for, like Akita mentioned yesterday, give this showcase to companies outside Brazil. Because the thing is, a lot of places are looking for good, talented people, and well, my past experience say that they having a good luck looking here at this country. So that's really amazing. Which leads me to Podium, which, by the way, is the place I work for. Podium, we brand ourselves as interaction management platform. That sounds very buzzwordy, but you can think as imagine all those online businesses. You know, they are very good and convenient, but still there are a lot of things that just works offline. Think like buying a car. There are things that maybe are you just prefer doing that offline, like buying clothing if you have questionable fashion choice like me, or like gadgets, maybe you want to test that. So what Podium does is creating this tool set where you can empower those businesses to keep connected with their neighborhood, with the places around them. So like you can give good ways to make reviews to Google Maps and Facebook, for example, so they may be found, and also have extra messaging capabilities so you still keep connected to your customers. A metric that I like to say from Podium is like 1 in 4. From all numbers in US, 1 in 4 is running through our platform, have some interaction with our platform, which is huge. If you want to know more about, is something that keep you interested, we are hiring. We just opened our office here in São Paulo. So we are looking for Elixir engineers, React engineers, UX designers, and product managers. So if it's something you want to know more, please come talk to me. But what I'm gonna talk today is not from Podium. Actually, something that happens on a previous job of mine, where I work for a company that do business in the telephone space, in VoIP space. So VoIP telephony in general is a very interesting beast, for to say. A lot of people have really, I'll say, strong feelings around this. The product specific that I work on, I would call just the product here, because I don't work at the place anymore, so I don't know how much I can say about it. But some of you may infer where the place is. The product I work on, what it does. Imagine this little cloud here. This little cloud is your application, and the product acts more as a platform for VoIP. So your application may send requests to our product, and from those requests, like call this number, for example, our product will actually call the number. So they will make this call happen and control this call. Eventually, those calls may have something interesting happening. Let's say the call was answered or is hung up or whatever funny thing may happen with that. And those events will be translated to webhooks to your application, so your application can react to that call and do like further commands. The two pieces of data that you need to keep in place for a product to work. One is the configuration of your application. Imagine the URL for the webhook. That's something that was very stable. When I say stable, I mean doesn't move too much. Like you configure your application, is done, oftenly. In the other piece of data is the call state, like things that are ongoing, so you know if like your command is valid or not. And our product run inside a cloud by itself, like a cloud provider. Think about like AWS, Google, Azure. And I think with clouds, like one of the constraints of our products is have 5 nines availability. And that's very hard to achieve. To have an idea, of 5 nines availability is about half our year of offline, being offline. That's as much as you allow it to have an availability. And that's very hard. And to be honest, this product's very young, so it's still not there, but that's our target. That was the number we are trying to reach. So one cloud was not enough for us because clouds may broke. So what you have is a multi-cloud setup. We have things running, like the numbers, the names I said, like Google, Azure, and AWS actually are running on all of them, and even on our own infrastructure. But, you know, clouds break. The magic, like the dream is not there yet, so the clouds may break, and we need to protect ourselves for that. Just to have an idea, at the beginning of this year, we have an outage of about an hour. So I say that we have at most half an hour. We have an entire hour out because Google has some issues with their router or something like that. And have a few lesser ones, but many on AWS and Azure as well. So our application was written in Elixir. And for that, we are able to leverage a lot of the powers that Elixir gives us. Like it's, for those who don't know, Elixir runs on top of the Erlang VM, which have this really good story about reliability, and that's one of the big things that we want. And still pretty fast. Our architecture, we are aiming to be as fast as possible. Imagine when you make a call, and for like whatever number, probably a customer support number, and that call like waits for a second, and you don't know if they completed or not. That's not a good experience. So like performance is very important. It's most important for telephony than for web, because you have stricter requirements, like stricter expectations around the quality of this. So our first iteration, our first design as application is like this, have this single purple node here. Imagine this is our VM running Elixir, and you have both our application, our code, and this is the smaller one, and the bigger one is our data. Our data is running inside the same node, and that makes things fast, but gives a lot of complications down the road, because then we not have like this stateless applications as we are used to work on. We have a stative one, and that's very, very hard to operate. Elixir gives a lot of, in Erlang, actually Erlang does, gives a lot of tools to deal with this scenario, but they are not so usual, and they're very specific for this technology. So that's not, it's not something that was able to leverage as much as we like in our infrastructure. So we made a plan to like fix this. The plan was like, we are trying to cut only the data and make a stateless service. Simple, right? That will help us with operability of our application, and we can like help with scale as well. But then comes the question, where we put our data. We thought a lot of different alternatives. Think about like Redis was fast, or can use some distributed thing, or some cloud like DynamoDB would be a good one. But the thing is, all those technologies require a lot of refactoring for us to just start trying. And we already have Postgres running. we know how to do Postgres, we know how to do SQL, like it's very familiar choice. So that's the choice we follow. And actually, Elixir has a really good tool set in form of Acto and Acto SQL to like really. It's not as plug and play because of our application, but like it was very minimal refactoring, and refactoring for something that is used broadly around the community. So Postgres is a SQL database. I believe everyone here deals with SQL sometime in life. Okay, and also it has this ACID transactions. For those who don't know, atomicity. A lot of all things that happen inside transaction should happen at the same time. Consistency is more an integer non-nullable field. It will not allow you to put a string there. It's this kind of consistency in ACID terms. Isolation, transactions should not bother with other transactions. In durability, you'll not lose your data. There are databases that lose your data. There are bad ones. Keep out of them. This is not as simple as this as it may look. If you watched yesterday's talk from Milhouse, you know some gotchas around this, but it's way better than have nothing. So that's something that we really look for. But our multi-cloud, multi-region, multi-replication scenario, how that works? Well, in Postgres, it looks kind of this. You have this your node. So imagine this box here is your database node, and this node I call it active, but another terminology is master follower. I'm using active passive here. You have this active node, and you have like a passive, which is a replica. So everything that happens in the active node will get replicated to the passive one, and your application needs always to reach for the active one. So it can't. There are a few setups that you can read from the passive, but usually you go straight to the master, the active, because only this database will allow you to make transactions to write data in. We can have like the setup. You can have multiple replicas, so you can have these multiple passive nodes, which works great for our setup of having multi-cloud. And how thus, when things went bad? Well, in Postgres, you have this kind of monitor process that will look over all the other nodes, and if somehow your active node dies, well, the monitor will talk to your application somehow. Really wave handling here, but you tell your application that it needs to like reconnect to another node. And it will also make one of the passes the new active. So that's how you do high availability in Postgres. But when I started working on that, we heard about this new fancy database called CockroachDB. And, well, a good thing about CockroachDB is all this, this new SQL wave, which is a fancy way to say that is a kind of middle ground between SQL and NoSQL, like trying to fit the best of both worlds. So it has this SQL interface. So you can like make queries and work with it in the same way that you do in Postgres, but it still has all these distributed capabilities that you only found on NoSQL implementations. So it's something that we think, oh, that's worth trying a shot on that. How does Cockroach do this distribution? When you talk about distributed systems, one of acronym that always pop up is CAP. CAP means consistency, availability, partitioning. Consistency here, bear in mind, is different from the consistency that we find on ACID. ACID is just that integer non-nullable thing that I mentioned. This consistency here is more if a node agrees that something is true, and you ask another node, all nodes you agree that this is true. You'll be the same answer, all nodes. Availability is no matter what node you ask, it always give you an answer. Maybe not the most up-to-date one, but it give you one. Partitioning is that it is able to survive fancy things happening in your network. Happens though, partitioning is a given, because it's not a matter of if, but a matter of when. And Cockroach, given its tries to be as close as possible to a SQL, as transparent as possible to a SQL implementation, it really trade-offs consistency. So sometimes your node may be not available. I will explain more further. To make this consistency happen, it uses a consensus protocol. Consensus protocol is a kind of algorithms and protocols that are used to achieve consistency in a distributed fashion. In very hand-wave way of describing, imagine that you have like this 5 nodes. Each one has their own state. And one of those nodes wants to make a change across the cluster. So wants to move 0 to 1, for example. To do that, it will communicate to all other clusters. You like broadcast this change. But if it needs to wait each node to answer back, that may take a lot of time, and may even not have these answers because somehow one node may die in the middle of this broadcast. So there's no way to know. So it doesn't wait everyone. It just needs a majority of your cluster to give you an answer. If the majority agrees, it's okay. Eventually, here's the hand wave part, your cluster will agree. In some you reach this state. But the thing is, always that you need to make changes, it always goes through this consensus. And sometimes, depending on your implementation, reading from your cluster also needs this consensus. But that's how I guarantee the consistency of your data. It's important when you have this NAT split. So imagine that these 2 nodes below are not able to communicate with 3 above. If some of the above nodes make this change is broadcast for all the ones that can hear it. 3 nodes is majority of 5, so they are able to work in a consistent manner. But if that happens on the other half of the cluster, it will not achieve, like 2 is not enough to have a majority of 5. So it just discard and probably error out. So that's the tricky part of understanding the availability and consensus trade-off. The consistency and availability trade-off. Like, it's not that your entire cluster isn't available, just part of it. But the part that is able to answer, you guarantee that you always give the right answer. Eventually the net split heals, and your cluster, you may be able to agree again on something. For the consensus protocol that Cockroach uses underline is Raft. The thing that I show is not Raft itself. Raft has a lot more moving pieces. But it's a really good one, industry standard, and they use a battle-tested implementation. That's the same one shared with etcd, with another database-ish software. It's not a database, it's more a service discovery piece of software. And how Cockroach uses those Raft implementations. It creates a concept. It uses a concept called ranges. So it's a thing entirely from CockroachDB. Ranges imagines a big blob of your data inside this database. This can be your table, can be your index, can even maybe your metadata about the database itself. You have this big range and this big blob of data, and what it does is splitting apart into smaller ranges. Those ranges span about 64 megabytes. So you have something bigger than 64 megabytes, try to split in half. And like getting one of those ranges, it's able to replicate that range across all your nodes. And the tricky part here, that's the secret sauce of them, the Raft protocol is implemented per range. So you don't have a consensus across all your data, but just between those ranges. You pick, because Raft has kind of a leader node elected to make the consensus work. Here I'm using Lisp because Cockroach has the concept of a lead and a leader. They are kind of different. There are very nuanced differences, but optimization is to be the leader of the group is the lead as well. So I just use the terms interchangeably here. And the thing is, this is good. This strategy of ranges is because like the distribution around your cluster don't need to match everything. All nodes need to be equally. May have different sets of data, and for each range may have a different node as the leader. So in the case of the Postgres that I showed before, you have the active-passive. This works more like a multi-active. For each piece of data, you may have a different server as the leader, the active. And how does a write work? So let's imagine do an insert data or an update. You do your transaction, how that will spread across the cluster. So imagine you have this 3-node cluster, which is the default one they recommend, because 3 is a good number, is a magic number for consensus to work. And imagine that your application wants to make a change to the green range, some data that's located on green. And let's assume that this request is coming to the same node that's the leaseholder of this range. So it has like the control of if things are okay or not. As the consensus, as I described earlier about consensus, what you do is just broadcast this change across the cluster for all the nodes that has this green range inside. And as soon as one of them, in this case, like the majority, answers, so 3, just one node needs to answer to have this majority. This change means that this change can be done and can be committed, and so you'll be returned for your application. But that is the best scenario. Another possible scenario is you're trying to make a change to a node that doesn't hold the lease for that range. So what will happen in this case is that this node needs to talk with the leaseholder. So you have this extra round trip. When it reaches the leaseholder, it then broadcasts back the changes across cluster because it knows what's the most up-to-date vision of your data. Works in the same way. This time the second node returns the answer. And then when you have this majority agree in the change, it can answer back. So it's the same scenario as before, but it has this extra round trip. Yep. And reads. Okay. Reads happen like the way it works, it can have some, because of these ideas, this advanced idea of leaseholders, and it can do some better optimizations in the read case. So imagine, again, the best scenario is I want a data from the blue range, and I'm going to the node that has the leaseholder of that range. Because the leaseholder guarantee that this data is the most updated version, it knows, it has the consistent version of your data, it's able to just answer. So it's way faster than the write case. But as the same thing may happen on the write case, if you reach a different node from the leaseholder, so in this case, let's say that we are querying the red range here, it still needs to ask for, no matter that it has some some red range inside it, it has data, it doesn't know if that's up to date. Only the leaseholder knows. So you need to ask leaseholder, and then leaseholder can answer back with the data, and then it can return. So if you're not reaching your leaseholder, so this is a thing in Cockroach, it's very important to optimize where the leaseholder is. And leaseholders can change, okay? But that's a very sensitive, like the latency between nodes are very, very, very sensitive, no matter how much optimizations they do. Scaling in failover, that's the thing that brought us to Cockroach at first time, because that's the problem we are most trying to solve. So let's imagine that you have this 3-node cluster again, and somehow we add a new node to this cluster. So we have this new node, and it has no data in it. The cluster will try to auto-balance the ranges across everything. So first you detect, oh, you don't have like the red range, for example. Okay, let's move it. And you do that till you have a cluster that has more or less the same amount of ranges. But what happens is some node like dies, like this Italy node dies. Well, then Cockroach detect that you don't have like the minimum amount of replicas across your cluster and tries to like do the reverse, like let's copy more, have more copies until reach the minimum amount of copies of your data that you want. So that's how it achieves the not only it's how it achieves this guarantee that you not lose your data. It's again, if you're using a database, you want to preserve your data. And having these ranges of data across your cluster well distributed is very important for one that I think is one of the more cool features that this database have, what they call in the documentation as follow the workload. Is more or less like this. Imagine that like this node, when you spin up a new node, you can add some tags to this node. They call it locations, I think. Here I just use like a region tag, but you can add whatever. You can like add like the region like this, you can add a provider, the city, no problem. But that's how it knows where it is and where the request is coming. So it can have this data spread upon the world. It's not really my map is not as aligned as it could be, but well, imagine have your cluster spread across the world, so different data centers. And let's imagine that your application has the most volume comes on business hours. So business hours in Europe would be way earlier than business hours here. So the cockroach should kind of detect that most of the requests are coming from this region, and we try to stick leaseholder close to that. The regions still need to connect themselves. So again, if you're writing data, this data needs to from Europe. It still needs to go to US and to South America. In my example, still need to go there. But at least like the reads will be optimized for that range. And if eventually like time zones shift, the day passes, and the South America region becomes hot. What? Thank you. The South America region becomes the hottest one, then all the reads still need to go to Europe. The CockroachDB will detect that, and then we move the leads to South America. So that's I find really cool. So because then can try to be as fast as possible. Well, I went a little fast. But well, my conclusions around this database is really cool. Did it solve us a problem? Well, the good sides is that it's very familiar, like using SQL to query your data, to change your data, and to use your tools that you use for like Postgres, for example, you can still use for CockroachDB. So that's really a good thing. And also help us to make to fast prototype this, because as I talked earlier, we already talking and doing this migration, going to a SQL database to Postgres. So okay, just changing the database URL to another one is easy. So that's really cool and really easy to test. And honestly has a little few moving pieces, because no matter how you have a lot of these nodes everywhere, Cockroach has a really good story around the setup. It's just a single binary that's spin up, so that's really good, and our operations team really thank us about for that. But unfortunately, as some of you may notice, the latency get very high. And as I mentioned, telephony has a really strict tolerance for latencies. When I say latencies are high, they may be about, in our task cluster, we're about 500 milliseconds. That may not sound too much for a web page, but is an eternity for a VoIP application. You need to keep under 100. That's our SLR. So because that, and no matter how much configuration there, like how much of the extensions that Cockroach gives in the SQL, because it extends the SQL dialect a little to give the knowledge about distribution. No matter how we tweak that, we are not able to achieve this low latency that we need for a problem. So unfortunately, this project, this database, we are not able to really use it, no matter how cool is that. So the cake was a lie. Well, maybe fault of us. We drink too much from the Kool-Aid because we are just looking at all this replication and how that will solve a lot of the problems in availability that we found. But maybe for your application, it's like the latencies will be just enough, and you'll be able to reap the benefits. Again, like the strong point in the familiarity. So like in using just to be a SQL interface makes it easy to test. So please, if you have like interest, give a try. But well, prepare for this high latencies. And that's it. Thank you.